Oh, it's a great pleasure and an honor to introduce Donald Saari to this distinguished audience. Donald Saari is first and foremost a mathematician, but his contributions extend to a number of other fields of scientific interest, such as dynamical systems, economics, political science, astronomy, and even cosmology. He was born and raised in Upper Michigan. He began his studies in Michigan Technological University and continued them at Purdue University in Indiana. His doctoral thesis dealt with the collision orbits of the Newtonian n-body problem. He then moved east to join Yale's astronomy department in postdoctoral position, returning, however, soon to Midwest again, this time for a longer spell, 3 decades in fact. He served as the head of the maths department at Northwestern University and subsequently its first Pankow professor of mathematics. He also joined the economics, applied maths, and engineering departments at the Northwestern University. In the year 2000, he decided to leave the Chicago area behind and move further to the west, namely to Irvine, California, where he is a distinguished professor of economics and mathematics. He has also served as a director of the Institute of Mathematical Behavioral Sciences at the University of California, Irvine. Don Saari's scholarly brilliance, although at times provocative and unconventional, has not gone unrecognized in the academic world. For example, he has 4 honorary doctoral degrees in the US and in Europe. He has been elected to the United States National Academy of Sciences. He is the fellow of American Academy of Arts and Sciences. He is the fellow of the Society of Industrial and Applied Mathematics. He is one of the inaugural fellows of the American Mathematical Society. And I'm proud to say that he has been elected an external member of the Finnish Academy of Sciences and Letters. He has been elected also as a foreign member of the Russian Academy of Sciences. And last but definitely not least, a celestial achievement in the year 2020, the minor planet named an asteroid 9177 after him. One might ask what makes a scholar trained in maths and astronomy to become an economist and social scientist in addition to his original fields of interest. In various interviews, Saari attributes the incentive to study economic and social sciences to the conversations he had with his students in lectures and seminars at Northwestern. He also became convinced that dynamical systems insights have a lot to give to his often relatively lower regarded disciplines. This conviction has resulted in a large number of articles in top-ranked scholarly journals and many heartbreaking books. Saari not only applies mathematical theories and methods, especially geometry and systems dynamics, to the social and behavioral sciences, he has importantly developed techniques motivated by the problems in those sciences. In fact, one of his recent books carries the title Mathematics Motivated by the Social and Behavioral Sciences. The relationship between individual and collective rationality has always been the primary focus of the social choice theory. As is well known, the scholarly community is divided on the significance of the paired comparisons of alternatives in determining the social choices. For a long time, the Condorcet-inspired scholars emphasized these types of comparisons seem to have an upper hand. Some 30 years ago, Saari entered the field and presented many results showing the fundamental unreliability of paired comparisons in the determination of socially optimal alternatives. Many a student of social choice field, yours truly included, started to revise, indeed reverse, their review on the Condorcet-inspired program. Yet many remain convinced by it. By the title of Saari's talk, I venture to guess that the all-important individual collective nexus is one again high on the agenda, as it should be, since it is the fundamental issue of not only the social choice, but all manner of aggregation of individual views or characteristics into collective ones. Don, we very much look forward to your presentation. The floor is now yours.
Thank you, Hannu. Thank you for the very generous and kind introduction. There we go. There we go. Yeah, what happens is, as I stated, actually, Hannu played a role in my getting interested in the mathematics of the social sciences. What I did is I was working, as he mentioned, in mathematical astronomy, evolution of the universe, questions like that, and a vocation was mathematics of the social sciences. And then I started reading some of the books there, and one of the books was to Hannu Nurmi. And reading it, I said, wow, there's a lot of good problems in here, a lot of good techniques and things. And so I moved into this area. Became my vocation rather than just an avocation. And when I moved into this area, I discovered really this complex tension between the individual and collective actions. And how do we handle that? Well, one of the ways in which we handle that is with game theory. And so it would be nice now if we could be able to take any game that is, the question is that can we take a game, any game that we have, and is it possible to take this game and to divide it so we can find the force causing the individual behavior and the force that's causing the cooperative behavior? For motivation, first, let's consider something that we all have, vectors. I mean, there's the direction of a falling star, the direction of a ball that's either thrown or batted, the fall line and scheme. And the trouble is that there's too many vectors, far too many to know each of them intimately. So what do? We take a couple of them and we get to know them quite well. You know, like for directions, we know the east-west direction. And that is to go to such and such a point, we don't need that vector. We'll go 3 miles to the east and 4 miles to the north. That is, we have an XY coordinate system. Now, this idea of taking competing forces and separating them so that they can be analyzed and studied is a standard tool in the physical sciences. The question is whether this can be done in the social sciences. Now, an example of this was Hannu's lecture of about 6 weeks ago, where he was talking about the tension between positive and pairwise and positive methods. And a message from his talk is that it's very hard to find answers because there's far, far too many voting methods to know all of them. One of the things which we learned from him, from Hannu, is that he could demonstrate all these problems by creating different profiles. So the question is, maybe if we got to know all profiles, a way to understand all profiles, maybe we can analyze some of these questions. That is, can we find a coordinate system for profiles? And indeed, we can. The first direction is I call the basic direction. This is just like going east on a vector. This is a portion of a profile where nothing goes wrong. Everything is fine. The pairwise and the positional methods, they all give you exactly the same ranking, not only the same ranking, but the same tally. Now, we know that this isn't true all the time. We know that there's methods where profiles where things go wrong. And so one of them is going to be in the direction of pairwise changes. That's characterized by the Condorcet triplet, which arguably should be a tie. Then what we do is we know that there's positional methods where there's changes. And this is given by this right here. And again, it should be a tie. Take a look. It's where one person has a preferences ABC and the other one has CBA, just the opposite. Now, the positional methods have no impact whatsoever on the pairwise changes on the green direction. And the green direction has no impact whatsoever on the positional outcomes. So by knowing all of this, we can start asking questions. For example, you have noise here. The rankings I have there should be ties. Are there methods that avoid these noise terms? And the answer is yes. The unique method is the board account. All right, well, Hanno asked a question, are there any Condorcet consistent methods? Are there methods that if there's a Condorcet winner, that method will have a winner also? And the answer is that, well, let's see, for Condorcet, you have to go in the basic and the green directions. Well, the border doesn't go in there. So the border is not the Condorcet consistent. And what happens is on that red direction, all the positional methods go in there and they can change the outcome. So no positional method is a Condorcet consistent method. What about our arrows independence of alternatives? Same answer, no positional method. So what we have then is the question I wanted to ask is it possible? Is it possible to find a coordinate system for game theory so we can do the same thing, where we can find out what's going on wrong and what's going right? And this is joint work with my former graduate student, Dan Jesse. And what we did is we said, can we find a coordinate system for games? That is, you give me a game, normal form or extensive form, you give me a game, and I can extract exactly the portions of the components, just like I did for voting, portions of the components of a game, which are Nash. That gives me the individual behavior. And orthogonal to that will be the group behavior. And in the third direction will be no impact. I'll explain what these are. So I'm going to explain all of these type things in terms of some examples. Let's start off, well, by the way, everything that follows in here is in a preprint with Katri Seberg. In fact, what happens is you can view this preprint that the two of us put together as a written version of what I'm presenting here. Let's start with the prisoner's dilemma. Now, the trouble with the prisoner's dilemma, when you see this here, you have to look at it for a while. You have to have some experience to look at this game and say, yeah, it's a prisoner's dilemma. Yeah, on the lower right, it's a Nash point. It's hard to see it's a Nash point because nobody gets anything, so why is it desirable? But let's look at it in terms of the decomposition. Because see, the problem is that the game combines the individual and group of behavior. And if we look at it in terms of the decomposition, the first part is the Nash part. Now take a look at the bottom right now. That's 2, 2. That one clearly is attractive. So you see immediately that that should be the Nash point. And in fact, in the decomposition, it turns out that no matter how many agents you have, no matter how many strategies you have, the Nash cell always has all positive entries. And so this is a desired point. So what happens is, take a look. In the upper left, there is a point that clearly is not desired. In the upper left is a point, and reflecting my work in dynamical systems, I call that a repeller. And why is it a repeller? Look, both players are being penalized there, -1, -1. So they both want to move in different directions to get out of there. This turns out to be the sole purpose, the sole explanation for the defecting of in the prisoner's dilemma. It's individual behavior, and it comes directly from this Nash component of the game. Now what happens is, let's take a look at the normal part, the group part. I call this the behavioral component. And this has group behavior, that's it. Now to see that it has just group behavior, that there's no Nash behavior in here, take a look and suppose that row goes up, top. Take a look at column's entries. What can column get? Doesn't matter what column does. The entry is the same, 4, 4. So in some sense, this game is posing an externality. Or suppose row goes down and looks at bottom. Nothing column can do to change the outcome. It's 4, -4, -4. But there are points, and the same thing if you look at it with respect to column. If column chooses something, column chooses right, then what happens is row will get 3 no matter what 3 does, etc. So now what happens is, but there are points which are desirable. Take a look, the Pareto superior point is upper left. But how can you get it? You can only get it from cooperation. For example, if row or if column goes to the left, row can do whatever row wants to do and still get the benefit of 3. And so what happens is cooperation is required. There's also a Pareto inferior point. That's where both players will be penalized if they handle that right there. So what happens here? What happens is that we see the tension. It just jumps at you, doesn't it? The bottom right, which is the lousy one for the group, is the best one for the individuals. And we take a look at the top left, which is very good for the individuals, is a lousy one for the individuals. So we see the tension for the decomposition. The tension just jumps out at you between what the individuals do and what the group can do. Now, this means also that what happens is, what's the usual definition of a prisoner's dilemma? They give you the A greater than B, greater than C, greater than D type things in terms of the entries. It means nothing. But here is really what the prisoner's dilemma is. When you look at the individual, at the Nash component, the Nash and the repeller are diametrically opposite. And take a look at the behavioral, the group outcome. What we have there is the Pareto superior point and the Pareto inferior point are diametrically opposite, but the Pareto superior is with the repeller and the Pareto inferior is with the Nash. You can extend this to any number of players, any number of strategies, and that is going to give you the essence of the prisoner's dilemma. What else can we get from here? Well, what happens is, what about tit for tat? Remember I told you about the player trying to, column trying to get the nice outcome of a cooperate. But row doesn't have to do it. Row's it can be a free rider. Well, not necessarily. What happens is you can just tit for tat. You move over to the right, and row is going to be penalized no matter what happens. And so what we have is, by extracting here, we can see all of these components, all of these issues of the prisoner's dilemma. They just jump right out. In fact, what happens is this is an externality. The behavior creates externalities, and this externalities is what this allows the tit for tat. Now, and then there's a last component here, and this is what I call the kernel. It's really all it is it's the average of payoff for each player. You take a look at the players, they get an average, they get a total of 8 well, you can add it up. I can't. 8, 4, yeah, 4, and so the average is 1, and so that's just the average payoff for each player. Now, let's talk about how in the world this decomposition comes about. Now, I would like to say that it came about through cleverness. Nah, it came about through a mathematical area called representation theory. Now, what is representation theory? Representation theory is a mathematical theory that takes a look at symmetries and puts them back into, in some sense, into a vector analysis. So you're allowed to get coordinate systems, and it gives you what is the unique decomposition. This is a technique which is used occasionally in research in physics, geology, chemistry, engineering, and on and on. That's how they're able to get some of these very intricate coordinate systems that separate the different competing forces. And this also happens to be a source of some of my voting material on how to handle some of these concerns. So the trouble is that the theory is quite complex. In my book, or our book on this right here, it's chapter 7. You can look at it if you would like, but it's complex. Fortunately, the complexity is just telling you how to do the division. Once you know what the division will be, the computations are almost trivial. Let me give you an example. It's a motivation for what the computations are. What happens is a student comes to you after you give an exam and says, I got an 80. How well did I do? Tell the student that the average is 70, and the student says, I did quite well. Tell the student that the average was 90. Oh, darn. So in other words, what we're doing is it's not the average or the grade, it's the difference from the average that matters. And the same thing happens in game theory when we do that. For example, let's take a look at this right over here. Suppose column chooses left. If column chooses left, then row has to decide between choosing 3 or 5. The average is 4, so we can write that as -1 + 4 and 1 + 4. So we have the difference from the average exposed there. And likewise, if column decides to go to the right, we have the average is -2, and so we have it written in this fashion. Now what happens is, in making the decision is not the 4. The 4, and this is what representation theory says, the 4 doesn't play a role in here, and so let's get rid of it. But if we get rid of it, we have to put it somewhere, so we put it in a new bimatrix to the right. Likewise, the -2 doesn't play a role, so let's put it over to the right. Now what we have is, take a look and see what we have there. I have rows entries for the Nash equilibrium, for the Nash component. It just pops out. We could do the same thing now to find what are columns entries. So I'll just do one of them. Suppose row chooses top. If row chooses top, then column is deciding between 5 and 7, or the average of 6. So therefore, the 5 is replaced with a -1, and the 7 with the +1. And that's the way we get the full Nash component. Now I have this new bimatrix I have here, and we know that's going to have the group behavior. So if I'm going to study group behavior, what am I going to do? Let's find the difference from the average. 4 - 2, it's going to be 3. The average is going to be 1. And so what you do is you just write that 4 as 3 + 1, and -2 is -3 + 1. So then what happens is the +1s, that isn't part of our analysis, and so the averages, so that'll go into the kernel. And what happens is the rest of the term gives you exactly what's going on in the behavior term. Simple, very simple. It comes from representation theory, but it's very simple. And really what happens is, it says that the decomposition is just this continuous sequence of finding the differences from appropriate averages. But from that, we get a lot of information. Let's now go and use this for some examples. How about Hawk Dove? All right, you got Hawk Dove. And we know that that is a strategic type thing. Take a look at the 2 Nash points. The 2 Nash points are Hawk Dove and Dove Hawk. 1, 7, you can see that this is a strictly strategic type analysis. Let's find out, but it's not. There's the Nash. Here's what the individuals are is driving the individual behavior. Let's go through this analysis one last time. Suppose column plays Hawk. Row has to decide between -3 and 1, and the average right there is going to be, the difference from the average is going to be -2 and 2. And so what we have is, you just by going through this subtraction thing, we have what is driving the individuals. And what's driving the individuals, same. There's no difference whatsoever. Because instead of the 1, 7, we got 2, 2, so something else is driving it. And so now we take a look at the behavioral term. And when we look at the behavioral term, what we have is the Pareto superior point is, that's the interaction effect. The Pareto superior point is down on the bottom right. And the Pareto inferior point is going to be up in the top left. Remember, this is how the players, in this case, the birds, interact. Doves interact. Clearly, the hawks do not. And so what this does is the behavioral term right away extracts what's going on. We normally think of it as, let's look at it in terms of the Nash equilibrium. Why? Because that's the tool that we have. But most of the information, I mean, in most cases, almost all games, the Nash component is trivial. You look at it and you see right away what's the answer. Take a look at that Nash term. You got 2 repellers and 2 attractors. The attractors are the Nash points. And so you can analyze that right away. The complexity of the game comes from the behavioral component, one that we normally dismiss, or actually haven't looked at. And so there we have this right here. And so it's a kind of a birds of a feather type thing. Hawks can't get along together, doves can. And we also see this term that came in, the externalities. The externalities that hawks impose on doves with a 3 minus 3. So the behavioral term captures all of these type components, information that we wanted to have. So let's go on to something where there is obviously combat, the battle of the sexes. You know, one wants to go to the opera, the other one wants to go to the football. And so there's, and just the title of the game tells you that this is a competitive game. Let's take a look though. Let's take a look at what will be the Nash point. The Nash point is what? The column chooses opera, then row has to decide between 6 and 0. That average is 3. So there you have the entries. 6 is 3 above the average, and 0 is 3 below the average. So we get the Nash point right away, the Nash component. And yes, take a look. Indeed, we see the competitiveness. That the person interested in football definitely wants football. That gets more pleasure out of it on an individual basis with the 3-1. But here is the behavioral term. And notice what the behavioral term shows you. The Pareto superior term is bottom left. What does that have? That shows that the group group gets a reward of some sense or another. If the person wanting football opts also for opera, and the person wanting opera opts also for football, if they're cooperating with each other. Very different than the usual interpretation. And so now what happens is what's bad is the Pareto inferior point, is if they really want what they want. If they go for, never mind the group, but I want my football, I want my opera. And so what we have then is a very different interpretation. We have, rather than battle of the sexes, we probably have cooperation of the sexes. And so that shows you again the type of information that can be extracted from a game on this all important individual versus group behavior. Now, let's take a look at the Stagnant. We know where this comes from. This came from Rousseau. And what does Rousseau have here? Well, let's see. Stag, you get the good reward. Now, if you're going hunting, you need a partner. If Hanno and I are going hunting, Hanno's a good shot. So Hanno's out there along the road with his trusty rifle. And I'm trudging through the bush, making noise and trying to chase the stag down across the road where Hanno can shoot it. But it's a rainy day. Come on, I want to go home and see the basketball game. And so what happens is I see a couple of rabbits and I shoot those and go home instead. And so that's really what Rousseau is trying to get across, the difference between cooperation and individual behavior. But this is also, Harsanyi and Sultan also picks up on this. Remember, what they do is they say, I have two Nash equilibria here. That's the top left and bottom right. And they say, look at the top right. That's a payoff dominant because it gives everyone more money or more utility or more whatever it is. And the bottom right one is risk adverse, risk dominant. Now, you remember what the definition of risk dominant is? Oh yeah, you can look it up, but you remember the definition? Let me show you how you can get it. What we do is here's the individual behavior, the Nash behavior. And take a look. What happens is the risk dominant equilibria is 2, 2. The product of that is 4. The product of the other one is 1. As proved in the book on this material, what happens is in a decomposition, no matter, you see, risk dominant is usually for 2x2 games because it's too complicated elsewhere. But in here, it becomes quite simple. And the decomposition has proved that a Nash cell is the risk dominant cell if and only if the product of its entries is the largest. And so we have that right there. And so if it's the largest, why not payoff dominant? Well, that obviously comes from only one place. I told you where the complexity comes from. It comes from the behavioral term. And the behavioral term, we take a look, what we have is the top left is the Pareto superior point. And the bottom right is the Pareto inferior point. And what we have here then is that cooperation gives you a reward. That's the top right. Going off on your own, the heck with cooperation, gives you a penalty. That's the minus minus. And so what we do is we have that there. What happens is that in general, this nicely captures the Rousseau story, the behavioral term, not the Nash term, not the strategic term, but the behavioral term. Nicely captures Rousseau's theory about the importance of cooperation. And what happens is, it is always true, no matter how many players or strategies you have. If you have a risk dominant term and the payoff dominant term is not risk dominant, it's always because of the behavioral term giving benefit for cooperation. And so the payoff dominant, rather than just giving more money or more utility, what it does is it gives you, it is a result of a reward of cooperation, which is a different interpretation for payoff dominant. And this is used in experimental games. Brian Kendall, another one of my former graduate students, what he did is, as Olga knows, what Brian did is, in a paper that'll be coming out shortly in experimental economics, said that, well, let's use this. Let's use this to find out how people behave. And how did they behave? Well, let's keep the Nash terms fixed. All the interest is in the behavioral term. And so he takes the behavioral term, take a look at it. I'm going to change it now. He changes it so that it is in general. So now he has a continuum of games. A continuum of games with the same Nash, but he can now play games with these betas to try to determine when people will do certain things in the stag hunt, and compared to what the theory says. Very nice stuff. Let's go on to 3 or more players. Now, I said this strategy, this decomposition, works for any number of players. And this right here is a legislator voting game. Not too interesting. I just mainly wanted to show it to you to show you how to make the decomposition. Now, first, what do we have here? They're voting for a salary increase. So if they all vote for yes, then what happens, and you see I have 2 bi-matrices there. because I have three players. I got row, column, and face. And the by matrix to the left, that's when face votes yes. The by matrix to the right is when face votes no. And so what we have here is we have the entry 222, all three of them vote for it, so they get the salary increase. But look here. What happens here is row says the heck with it. Row votes no. Vote, and it's much better off because why? The salary increase is still there, wins by a majority vote. But now row can go to the voters and say, hey, I voted against the salary increase, so vote for me. Of course, what happens is there is another entry over here that's 000. That's where they unanimously vote against it. And so it fails. And then there is another type of entry. And this one right here is where face votes for the salary increase. Column and row vote against it. And so now face has to go to the voters and explain why he voted for a salary increase that was defeated. Now, what I want to do is to show a primary thing I want to show you here is how do we get the decomposition. Okay, so let's take a look at, we have the decomposition right here. And if you notice, it is only Nash and repelling cells. So there are 4 Nash cells here and 4 repelling cells. Now, what happens is, let's take a look at this entry right here in the upper left. That is where column votes yes, face votes yes, and row has to decide between 2 and 4. Well, the average is 3, and so there we have those entries, the difference from the average. Now let's take a look if column votes yes, face votes yes, and therefore we take a look at what is column's decision. It's between 2 and 4. Again, the average is 3, and so again, there we have the entries. And the last possibility is if what happens is row and column vote yes, and now we have to see what is face going to do. Well, face has to take a look between those 2 entries, one on each of the bimatrices, and we have the entries, and we have that right here. So therefore, for any number of players, the same strategy goes through, just a little bit more bookkeeping, but it's still the same. And then what we have is the behavioral type. Now what happens is there is something here. Take a look at the Nash term. On the second bimatrix, bottom right is a Nash point. Repeller is diametrically opposite on the other bimatrix up in the top left. Where's the Pareto superior point on behavioral? Just in conflict with it. So this is a form of the prisoner's dilemma, which comes out quite quickly if you look at it in terms of this decomposition. And what we have then is this raises concerns, such as with the prisoner's dilemma, as how can we get the cooperation? And that's really a big theme. How do you get cooperation? Well, in experimental evolutionary game theory, they say that cooperation requires punishment. We get that for free. Take a look. Here's the Nash component. Nash component, easy, nothing to worry about. You get it, it's trivial to analyze. To the right is the behavioral component. And what happens is, let's suppose cooperate, it's right there. You know what can happen. You know that if column chooses to cooperate, row has no penalty whatsoever. You do whatever row wants and be a free rider. But the sum of the entries for row has to equal 0. So one of them has to be negative. And so what we can do is tit for tat always as possible. And now suppose we don't want tit for tat. Well, what we have to do is we have to make the behavioral Nash-like, so that there are reasons to do this. One approach would be to add, as I wrote right here, is to put a penalty if you don't cooperate. And where do we see this? We see this in Tom Schelling's books, where he talks in his early books in terms of these different types of behavior. It's all in terms of the behavioral term. if you analyze it with the decomposition, and you see that he's talking about imposing a penalty on the behavioral terms. He doesn't use those terminologies, of course, because this theory hadn't been developed yet. Or what happens is you're driving along the highway, you're talking on your cell phone, you get pulled over, you get a penalty for not wearing a seatbelt. It's standard. And then what happens is you could reward good behavior, just like in kindergarten or nursery school, you get a nice little bonus if you behave well. So in either case, what you're doing is if you aren't using tit for tat, the approach is to make it Nash-like, not just punishment, but to make the behavioral term Nash-like, so that it is self-enforcing. And really, as I all the way through here, the complexity of the game and everything else comes from the behavioral term, and cooperation has to involve the behavioral component. And what happens now is let's talk about the design of games. Here is a game. Start with Nash, and then add a component. And what happens is you get this simple one. Look what I have here. I have a simple game. Look at the game on the right. You take someone who's never seen game theory, and you tell them, you go your row, you have to choose either top or bottom, and you get the right reward. They're going to choose, they're going to find the Nash point there right away. And one of the reasons is there's no conflict. Take a look. The Nash point is top left, and the Pareto superior point is top left. The bad point is bottom right for both of them. And so there's no conflict, and that's why it's so trivial. But suppose I add a more complicated behavioral term, and I get this. And you ask them to try to find the Nash. Well, that's difficult. And in fact, McKelvey and Palfrey, what they did is they said, let's analyze this. Let's say that, that there's a level of complexity that is involved. So they invented this quantum response equilibrium. And what was the theme behind it? It was a beautiful theme. It was that let's say that we have an individual, and we have not only group interactions, but we have the ability of individuals to make decisions. And they got their approach coming from Duncan Luce, from his work on the choice axiom, which led to logit models and everything else. So from that, what you can do is you can compute the complexity. Beautiful idea, except it doesn't work. The trouble is that if you apply their theory to these two games that I have here, you get exactly the same analysis, exactly the same level of complexity. When it's clear they're not the same level of complexity. Why? Well, what happens is that once you do best response analysis, which is what you need if you're going to talk about that, what are you going to do? You're going to wash out the behavioral terms. The top and the bottom of the behavioral terms are the same. So they're going to cancel. And this also works for a large number of other areas where we talk about best response, like K-level thinking. And so what happens is we run into a very important issue. The issue is what makes games more complicated? The behavioral term. What tools do we use to analyze games? Best response. What happens with best response? It washes out exactly what causes the complexity, why we wanted to study the problem in the first place. And so now as a last topic, I'm going to talk about finding mixed Nash equal. None of us like that. Come on. I'm a mathematician. I don't like finding that. I mean, look, to find it, I have to assign probabilities, Q1, Q2, Q3, and I have to, what am I going to get? I have an equation, Q1 plus Q2 plus Q3 is 1. I got, for mixed Nash, 4 equations and 4 unknowns. I'd rather go mow the lawn or something like that to solve equations. But wait a minute. Didn't I tell you? I told you that all the Nash information is right here in the Nash component. And take a look, how do you get that Nash component? Look at the Q1 column. Row has -6, -5, -4. The average clearly is -5. So therefore the entries are -6 is 1 below the average, -5 is at the average, and -4 is 1 above. So there we get the Nash entries, they all go that way. Now what happens is I write down use the Nash component and I write down my equations. So now I have 4 equations and 4 unknowns. Let's add them up. And what do you get? You get 0. I find one of the values. And why is it 0? Well, take a look at the Q1 entry of those equations. What about the components? I'm adding 1, -1, 0, and 1. I'm adding the differences from average, so they have to be 0. That's true of every single one of those rows, so we get 0. Even more, since the sum of the equations is 0, I know their dependence. I can get rid of one of the equations. So now with this one right here, I reduce it down to 2 equations and 2 unknowns. That isn't too bad, but it sure saves a lot of work. Okay, and so this provides a small flavor of what can be obtained with the decomposition. Let me give you some references. For the voting type theory, that a lot of it was developed in Basic Geometry of Voting in '95. But a more readable source is the Chaotic Elections, which I was asked to write for the American Math Society, which is, don't look at the American Math Society, it is the expository type. And then Hanu, what he did is, I think that's 2003 rather than 1999, but he took some of this geometry that I developed and he applied it to an actual election outcomes. Very nice. The book that has all the information is right here, Jesse and Saari. It's coordinate systems for games, and it's Springer. And then if you're interested in the quantum response equilibria, that's the first paper in the issue of Journal of Mathematical Psychology. And then the preprint is that Katri and I wrote, Tools for Game Theory. And with that, I thank you for your patience and ask any questions.
Well. Thank you very much, Dan. Brilliant.
The important takeaway. Oh, go ahead.
I was this game decomposition is somewhat familiar from your papers to me, but I was just wondering about its relationship to the profile composition that you used in the context of social choice. Is that I mean, which one came first, the game composition or profile composition?
Profile. This coordinate system for games is recent. It's about 2015. And as you know, that the decomposition I have for profiles and for voting goes all the way back to about 91.
Okay, so.
And
right, yes.
But the idea is the same. It's to try to find the symmetry.
Yes.
If you find symmetries, then you say, aha, there's more information I can make. I can separate behavior. And as you know from the chaotic election book, I identify, for example, you look at the Condorcet triplet.
Yes.
And you change the names, you get the Condorcet triplet back. And so really what happens is there's a symmetry there. And so by looking at the symmetries, you're able to extract all of these type behavior. And so I wondered if the same thing could happen for game theory. And game theory, what is the symmetry? The symmetry is a surprising one. It's that if you have a game, you can interchange the rows, and the game is exactly the same.
Mm-hmm.
Well, that happens to be a symmetry. What are the consequences? And when I looked at the consequences, we found out there's a lot. Surprising, heavy consequences.
Well, Don, I have a question. You have this behavioral part and the Nash part, so to say, and the Nash part, doesn't that describe behavior as well?
No,
I mean,
the Nash part strictly has all information and only information about what individuals can do. What is the advantage for individuals? The behavioral part has all information and only information about cooperation, coordination, externalities.
Mm-hmm.
And really what happens then is this conflict between individuals and groups is really captured by the difference between the Nash component and the behavioral.
Mm-hmm. Yeah, but I'm thinking about behavior, you know. I mean, you behave as an individual on the one hand, then you know you're in the Nash part. Eh?
Yeah, if you're
Or-
looking at it strictly from my what I want and I want and I want that only, yes. But once you start saying, "Oh, wait a minute, what's my opponent thinking?
Mhm.
My opponent doing?" That's the behavioral term now. And
Yes.
so, as soon as you start throwing in anything about thinking about the other players, which is what coordination, cooperation, all of these things.
Mhm.
That is the
If it's
rewards and penalties you're going to get from the behavior.
if it's going to be repeated or something like that, obviously in a one-shot game you're going to end up in the Nash component. But if you're going to have a repeated game,
I disagree with you, Kathy.
oh, okay.
That's
No,
not
no,
true. It's you take a look at the prisoner's dilemma. You do not get to the Nash point at all.
Yeah.
What happens is the behavioral term plays a big role when we have iterated. But what it also does is it says that if I'm analyzing this game, you run a lot of experiments. And so
Mhm.
when the students, subjects are analyzing the game, what happens is the behavioral term is playing a heavy role in that analysis. We see this in the hawk dove, we see this in the stag hunt, in all of them. That
Mhm.
why are we doing this? Well, actually, it's not the Nash at all. It's behavioral tactics.
Yeah. No, but I want, you know, I wonder about the decision maker. Actually, the decomposition is made by the decision maker in a way, you know. So he
No,
has to.
it comes directly from the game, from the form of the game.
Yeah.
So if you
It's a
give me,
form of the game, but if you are in this game, you know, then you have to decompose in a way.
no, it's a unique way. It's I have no power of changing the decomposition. What happens is you give me a game. I
Yeah.
don't care what game it is. You give me a game, no matter how many players and how many strategies. What happens is the decomposition follows from representation theory. It's unique. There's nothing I can, none of my input can be put in there. That is what it is. And so therefore, it's just like you have a vector. I can't
Mhm.
change the x direction and the y direction of the vector. The vector determines it. And so the same thing right there. You're given a game. You cannot determine. I mean, you can compute what it is, but you can have no input on what's going to be the behavioral term and the Nash term. It is just like finding the x direction of a vector.
Mhm. I don't think we disagree, but I'm thinking really about the person who makes the decision, you know. He has to know it, you know, this decomposition. Huh?
No, they don't know the decomposition.
Yeah.
What happens is, see, the decomposition is something that can be used to explain behavior.
Mm-hmm.
What happens is, you take a look at the experiments. Some experimental economists on here, including Katri. And what they do is, the students are given a game. They want to make money. And what happens
Mhm.
is the behavior, that's their behavior, that's their decision. The game has, if you want to explain why did they do certain things, like
Mhm.
Ryan Kendall did, what you're doing is you're decomposing the game to saying, here's why people are doing such and such a thing.
Okay.
But I think what Manfred's trying to point out is they have to somehow, if they don't know the decomposition, at least they have to understand that there's a conflict between the group and like that one example that you showed where there's no conflict, the Nash is the best outcome. Then it's a really easy thing to put in experiments. But if you do have some sort of conflict, then you might see people
It's better.
internalizing to some extent.
Yeah.
Yeah, this is the issue. Thank you.
I just want the same question, but simpler, as was asked. So in the behavioral part, in the cooperative part, why do they still have variation in individual payoffs conceptually? Shouldn't it be like equitable allocation of social welfare or something?
It has to come from the game. You give me a game, okay, and what happens is there's no. It's just like you give me a vector, and I can find the x and the y direction. You give me a game, and the features of the game tell you what's going to be inside the behavioral term.
Right, but who's the agent collecting those things?
The agent that designed the game. You design the game.
No. In each cell you have players, right? But
You
do
have
these players actually collect those payoffs?
No, the players look at the game, the sum of the three components, and what the decomposition does, it's just like if you have vector analysis. Looking at vectors is hard, but if we can find the decomposition, we can look at how much is going in the east, west direction, north, south, and it becomes much easier to understand. So really what the decomposition of the game does is the following. It says you have a game, and the players do something, and you're trying to figure out what in the heck did the players do. Well, what happens is the decomposition says, well, here's a part that influenced their selfish interests, the Nash part, and here's a part that influenced their group thinking, their group thought. And what happens is it divides it into these two different parts. So it's a tool of analysis rather than what the agents are actually doing.
Right, but I need to see the agents to kind of work with the incentives. So is it possible to say that as a player in the game, I am getting this much from individual rationality, and this much is the windfall from the society leaning my way today?
Precisely, nicely stated.
So why would I want to turn the wind away from my benefit behaviorally?
Take a look at the prisoner's dilemma. Why do you want to cooperate? Because what happens is the prisoner's dilemma, the cooperate term, it comes directly from the behavioral term. So why do I want to cooperate? Or in Stagnant, why do I want to hunt stag?
Well, I don't want to cooperate.
The extra points, the extra benefits you get from the behavioral term is what make those terms attractive.
So what compels me to change my strategy? What in the behavioral component compels me as an actor to change my strategy? Because eventually I have to be the one to change the strategy.
That is correct. And what happens is you say, whoa, I'm getting a bonus from this behavioral term by cooperating. So I'm going to cooperate, whereas I normally would.
Okay, I feel that I'm almost getting this done. Thank you.
Get the paper from Katri, and if you have any
Katri will fix my head. Yeah.
And if you have any questions, Olga, just let me know.
Yeah.
Sure. Well, everybody's satisfied. But I have to read your papers, honestly. I heard this decomposition already. You presented it somewhere, and I heard it 2 years ago and I didn't understand it. So I think now I have to start rereading it. Okay. So Katri, I will come to you and you will send me the paper. Will you?
In my experience, you have to read Don's papers several times in order to.
Yeah, I'm ready to read several times, and I really enjoy it to listen to you.
Yes,
you know that.
Yeah.
But it's not, well, it's somewhere in the title it says complex, so it's okay. So, well, there's nobody wants to discuss anymore. So thank you very much. It was a great session. I mean, it was really great.
Absolutely.
And I enjoyed it. Well, very inspiring. Very, very inspiring. So
Yes.
thanks, and come again.
Yes.
Yeah. Hanno, maybe you want to add something?
No, well, yes, of course, I was thrilled by this presentation, and occasionally I get this feeling that that was related to something that I learned before, and I've read some papers on this topic as well. This sort of deepened my understanding of those papers, but I probably need to do some more reading before I fully understand what is going on here.
So, Hanno, we will study it. We will study it. Okay.
We will, indeed. I'm sure you will, and I will definitely. Yes.
And then
one of the first places where I gave a presentation on this was at a conference that you ran.
Oh, yes. Yes.
And I was there, I'm sure.
You were there, man. Yeah.
Yeah. No, it's very lively and vivid with me. And I think at that moment, in a week after I understood it, but it's gone again, in a way,
Yeah.
So.
Yes, there's so many things done. But can you give me the reference about this preprint that you mentioned here? Is there a publisher already?
I don't know what Katri did with it, but Katri has it.
Katri, is Katri still with us?
Yeah, I'm still here. Sorry.
He was moved.
Yeah, I haven't heard. I haven't had any response for it yet.
Okay.
So thanks again. We close the session. It was wonderful. And we see it next autumn, again, I'm sure. Think about the topic already.
I understand that there was...
Okay, thank you.
Okay, thank you. Bye now. Thank you.
Bye.
Thank you. Bye-bye.
Why is